Hey there. Imagine a battle where one side's most advanced tanks keep breaking down, while the other's reliable machines roll on without fail. This was the shocking reality revealed in North Africa in February of 1943. A captured American M4A1 Sherman, painted with a hastily added German cross but bearing the name, War Daddy II, proved to German engineers that American industry had achieved a level of automotive reliability they had yet to master. How could a machine designed for mass production outperform German tanks in durability and operational endurance? Why did this single tank's flawless performance shatter long-held beliefs about German engineering superiority? Could it be that the secret lay not in cutting-edge technology, but in the relentless pursuit of practical, dependable manufacturing? And what did this mean for the future of armored warfare? In this video, we'll trace the astonishing journey of War Daddy II from battlefield capture to the testing grounds of Kummersdorf, unraveling how American industrial strength, rooted in civilian automotive principles, challenged and ultimately surpassed German technical ambitions. The most revealing truths about wartime innovation, and the critical importance of reliability, are about to be uncovered, starting right now. In mid-February of 1943, amidst the vast and unforgiving sands of Tunisia, a remarkable event took place. An American M4A1 Sherman tank, bearing the faint remnants of its star insignia beneath a hastily painted German cross, came to a halt in the desert. Its movement had been halted by capture, yet the tank itself remained fully intact and operational, a rare and significant prize in the chaos of the North African campaign. Around this captured vehicle, officers from the formidable Panzer Battalion 501 gathered, their notebooks already in hand, eager to examine this unexpected artifact of warfare. This single, well-preserved American tank, seized during the climactic Battle of Sidboid, would go on to ignite a profound crisis of confidence among German engineers. The implications of this encounter would resonate deeply within their design and development programs for the duration of the war. It was not merely the firepower or armor of this vehicle that posed a challenge, rather, it was the remarkable reliability and consistent performance of this machine, traits that the Germans had historically failed to prioritize. Its automotive engineering, exemplifying a level of quality and resilience, refused to break, regardless of terrain or conditions. The tank was emblazoned with the name, War Daddy II, on its hull, a name that symbolized its formidable presence. Its serial number, USA 3,676,401, indicated that it was produced by the Limer Locomotive Works. This particular tank belonged to Company G of the 1st Armored Regiment, part of the 1st Armored Division, a testament to the vast industrial capacity of the United States. After its capture, personnel from a German reconnaissance unit drove War Daddy II across approximately 350 kilometers of North African terrain, a journey that spanned over 4.5 days, culminating at the port of Sfax. Every mile of this trek revealed unsettling truths to the Germans about American industrial and engineering capabilities. The engine exhibited no signs of overheating, an issue German tanks often faced under prolonged use. The transmission remained flawless, performing consistently without failure. The final drives, critical components responsible for transmitting power from the engine to the tracks, maintained their performance without faltering. German tank crews, long accustomed to frequent mechanical breakdowns, even during short movements, watched with growing unease as this American vehicle effortlessly navigated through rough terrain and adverse conditions that would typically have disabled their own machinery. The reliability of War Daddy II defied their expectations and challenged their assumptions about the quality of American manufacturing. At the port of Sfax, The tank was carefully loaded onto a cargo vessel bound for Germany. The order from the Army Weapons Office was unequivocal. This tank had to reach the testing facility at Kummersdorf, intact and fully operational, to serve as a benchmark for American tank production and engineering. Although German intelligence agents had received scattered, fragmentary reports about American vehicle production, it was only when they saw War Daddy 2 in the flesh that the reality of American industrial strength truly sank in. The Sherman was not just a machine. It embodied mass production on a scale that Germany could not hope to emulate at that stage, built with automotive engineering principles that the Germans had yet to master. As the vessel steamed across the Mediterranean towards Germany, Wehrmacht engineers and scientists began preparing intricate testing protocols designed to uncover the true limits of this American technology. The process was not merely academic. It was driven by a reluctant recognition that their own vehicles, often plagued by mechanical failures, might be inferior in reliability and durability. The spring of 1943 marked a turning point. At the Kummersdorf Proving Ground, located in the outskirts of Berlin, German engineers would put this captured tank through a series of rigorous tests to analyze every aspect of its construction and performance. The tank, designated Zugfahrts 259 and bearing the German license plate WH058941, was carefully transferred onto a railcar for evaluation. Skilled German test engineers had already marked the surface of the tank with detailed measurements, thickness of armor, angles of sloped surfaces, meticulously preparing for a comprehensive examination. Kummersdorf, a renowned military testing facility situated approximately 25 kilometers south of Berlin, served as the primary site for scrutinizing both German and Allied equipment captured in the field. Here, in this meticulous environment, engineers would measure, test, and analyze everything from track tension to transmission efficiency. They documented each finding with precision, knowing that the results could reshape their understanding of armored warfare and influence future German tank designs. Every detail, every performance metric, was carefully recorded, as the Germans confronted the reality that the American manufacturing approach, driven by mass production, automotive excellence, and relentless reliability, was fundamentally different from their own. This encounter with War Daddy 2, a symbol of American industrial might, was more than a simple victory of capture. It was an awakening. A stark reminder of the technological gap that the Germans faced, a gap that would define the strategic and technological contest between these two nations for the remainder of the war. Their findings in exhaustive technical reports, meticulously documenting every detail of the extensive tests conducted. The Sherman was on the verge of undergoing the most thorough evaluation of its kind, a comprehensive assessment devised by the pinnacle of German engineering intelligence. A team of highly skilled engineers from multiple specialized divisions meticulously examined each component, leaving no detail unrecorded. They captured photographs from numerous angles to ensure every aspect was scrutinized, measured spatial clearances with precision instruments, and carefully documented construction techniques that, quite surprisingly, appeared remarkably simple and straightforward when compared to the more intricate German engineering standards. Among all the systems examined, the transmission immediately drew intense interest from the German powertrain experts. While German tanks typically employed straight-cut gears, a design demanding tight tolerances and requiring regular, meticulous maintenance, the Sherman utilized a different approach. It incorporated herringbone-cut gears, a design that had been a staple in American automotive manufacturing since the early 30s. These gears were capable of distributing operational stresses across multiple teeth simultaneously, significantly reducing wear and tear. This design choice, while seemingly less complex, offered exceptional durability and reliability, and did not demand the extremely precise manufacturing tolerances that German engineers considered essential. Initially, German engineers had regarded the use of herringbone gears as a manufacturing challenge that would be prohibitive given their existing industrial capabilities and workforce expertise. They believed that producing such gears in large quantities would be impractical, perhaps even impossible, without significant adjustments to their production methods. Meanwhile, American manufacturers had been producing these gears by the thousands, refining their techniques over years and demonstrating their viability in real-world applications. The testing process began with fundamental automotive trials designed to push every mechanical system within the Sherman to its limits under controlled conditions. Engineers drove the vehicle through a series of obstacle courses designed to mimic battlefield terrain, carefully measuring fuel consumption, monitoring engine temperatures, and recording the operating behavior of the transmission under diverse loads and challenging terrain. Following each test, the team disassembled key components, such as the transmission, engine, and suspension, to analyze wear patterns and identify any signs of stress, lubrication issues, or potential weaknesses in the design. These results turned conventional German tank doctrine on its head by revealing that the Sherman performed adequately across all critical metrics, and in fact, surpassed expectations in a key area where German tanks consistently struggled: operational endurance without requiring constant maintenance. The tests showed that the American design, particularly in terms of durability and ease of maintenance, was remarkably resilient in real-world scenarios, even when pushed to the limits. A detailed examination of the powertrain highlighted fundamental differences in design philosophy that, in turn, shed light on the broader divergence between American and German engineering approaches. The Sherman's transmission system featured 5 forward gears along with a reverse gear, with synchronization present on gears 2 through 5. This synchronization meant that drivers could shift gears smoothly without the need for double clutching, a process that involves momentarily disengaging the clutch twice during gear changes. As a result, operating the Sherman was almost as straightforward as driving a civilian automobile, requiring only basic driving skills. Contrastingly, German tank drivers had to master complex double-clutching techniques and manage throttle inputs with great care to prevent damage to their transmissions. German engineers believed that such intricate procedures were necessary to achieve optimal performance, presuming that only highly trained specialists could operate these tanks effectively. On the other hand, the Sherman's design accepted that ordinary soldiers with minimal automotive training could operate these vehicles comfortably and reliably. This fundamental difference reflected a broader strategic philosophy. American design prioritized ease of operation and robustness, while German design emphasized precision engineering and specialized skills. The heart of the Sherman, the Continental R975 radial engine, demonstrated exceptional resilience and adaptability to a wide range of operating conditions. Engineers observed that this engine maintained consistent, reliable performance across various temperature ranges, something that German engines of comparable power would often struggle with, either overheating or losing efficiency under similar conditions. The engine's tolerance for temperature fluctuations, load variations, and different environmental factors underscored its robustness and suitability for diverse combat scenarios, further contrasting it with the more fragile German power plants that often required meticulous care and precise operational conditions to function optimally. Power, in its many forms, was the underlying force behind technological and military advancements during this period. One of the seemingly straightforward yet highly effective innovations was the cooling system designed for armored vehicles. Although its construction was simple in appearance, it proved remarkably efficient in actual operation, ensuring optimal engine performance even under harsh conditions. Likewise, the air filtration system installed in these tanks showcased a remarkable resilience to environmental challenges, particularly the relentless desert sands encountered in North Africa. Unlike many of the German tanks operating in those arid regions, which frequently suffered from clogged filters and reduced boiler efficiency, these systems maintained their functionality over prolonged periods, reflecting a design ethos that favored practicality and robustness above all else. Every component of these vehicles was a product of a consistent design philosophy that prioritized real-world usability over intricate, often theoretical, optimizations that could compromise reliability or ease of maintenance. On a specific day, June 6 and 7 of the year 1943, the Hillis-Lean artillery range became a focal point of testing and demonstration. It was here that Albert Schaar, the Reich's Minister of Armaments, arrived to oversee a significant weapons development conference. This gathering brought together key figures from the armaments industry and high-ranking officers of the Wehrmacht, all eager to evaluate new technological capabilities. A central part of the event involved comparative trials, specifically, hill climbing tests, designed to assess the performance of German tanks against captured Allied vehicles. These demonstrations aimed to reveal insights into how well German engineering stacked up against the equipment used by their enemies. Among the vehicles showcased was the formidable War Daddy II, which sat among the latest German tank designs. This included a newly produced Panther ACEF Diem tank, a model fresh from the assembly lines, and a Ferdinand tank destroyer, representing the zenith of German armored fighting vehicle technology at that time. Schaar, who held the critical responsibility for German armament production and reported directly to Hitler himself, needed first-hand knowledge of what the American industry could produce. Equally important was understanding how German tanks compared to their Allied counterparts in terms of design, capability, and operational efficiency. The day's demonstrations revealed truths that neither Schaar nor the German tank designers wished to face openly. The Sherman tank performed notably well during the hill climb. It ascended the test slope smoothly and reliably. Its manual transmission, with 5 forward gears, shifted seamlessly from 2nd through 5th, without any hesitation or delay. The engine delivered steady power throughout the climb, and the tank's driver maneuvered it with apparent confidence, an ease of operation that would come to define the Sherman's reputation. In contrast, the Panther, equipped with a more powerful Maybach HL 230 engine producing about 700 horsepower, struggled to match the Sherman's performance in this specific trial, doing so only just and with noticeably more exertion. The Ferdinand tank destroyer, a technically sophisticated behemoth weighing in at 65 tons and boasting an electric transmission system, faced a starkly different outcome. It stalled partway up the incline, unable to complete the test. Witnessing this, Speer, an observer and later memorist, saw recovery crews scramble to restart the massive vehicle. The failure, occurring in front of dozens of senior officers and key industrial leaders, was embarrassing to say the least. Years later, in his memoirs, Speer would reflect on the capabilities of the Sherman tanks he had observed during his inspection tour of Italy in October of 1944. He noted that reports on the Sherman's off-road mobility had been consistently positive, describing the tank as capable of climbing mountains that German tank experts typically regarded as inaccessible to armored vehicles. Speer attributed this impressive cross-country performance to the Sherman's notably powerful engine, especially in relation to its weight. This gave the Sherman a level of mobility across uneven terrain that, in many cases, surpassed that of German tanks, an observation echoed in reports from the 26th Panzer Division, which emphasized this advantage in their field assessments. The significance of these findings resonated deeply within Wehrmacht circles, carrying considerable weight. The official public evaluation appeared in the widely read newspaper Das Reich on June 27, 1943. The article praised the Sherman as a remarkable achievement of North American technological laboratories, describing it as a praiseworthy product stemming from the North American steel industry. It highlighted that the initial features of the tank, particularly its mobility and reliability, were among the first aspects to draw attention, suggesting that the innovations embodied in the Sherman represented a noteworthy advance in tank design at that time. During the intense period of wartime development, American engineers embarked on an ambitious project to rapidly produce tanks that not only met but exceeded the demanding standards set by the North American automobile industry's reputation for quality and reliability. This effort was characterized by relentless serial construction, ensuring that each new vehicle incorporated lessons learned from the previous models. An illustrative example of American ingenuity was the creation of a gyro-stabilized gun, heralded as the first of its kind in the world, proudly acknowledging the United States' pioneering advances in this innovative technology. These public declarations, carefully crafted to serve propaganda purposes and to project confidence without revealing underlying concerns, subtly concealed the growing unease within German engineering circles. While German military circles publicly emphasized the adequacy of their tanks, internal assessments revealed that American armored vehicles were far superior in terms of engineering robustness, especially for prolonged operations in the field. At the testing grounds near Kumdorf, engineers diligently conducted systematic and rigorous assessments throughout the summer and into the autumn of 1943. Their goal was to understand the true operational endurance of the American Sherman tank by subjecting it to extended trials that pushed its limits to the maximum. The results painted a striking picture. The Sherman's operational range surpassed 2,000 kilometers before any significant maintenance was required, a performance roughly 4 times greater than what early models of the Panther tank could sustain under comparable field conditions. Further detailed measurements showed that the Sherman's drivetrain maintained transmission efficiency at levels higher than any German tank of the period, with substantially lower power losses through the transmission system. German tanks, such as the Panther, suffered from inefficiencies in their powertrains, which hindered their operational reliability. The American tanks featured a synchronized manual transmission, which made gear changes smooth and straightforward, eliminating the need for double clutching or delicate rev matching procedures that were obligatory in German-designed vehicles. Such design choices greatly simplified in-field repairs and maintenance. Another critical aspect was the design of the final drives. The German Panther tanks utilized final drive systems derived from the Tiger design, which incorporated straight-cut gears housed within structures that were ill-suited for the enormous stresses imposed by a 35-ton vehicle. These configurations proved to be a significant weak point. Reports from German mechanics fighting in North Africa and on the Eastern Front frequently documented failures in the final drives, often leading to the abandonment of Panthers after short movements of less than 100 kilometers. In stark contrast, the Sherman's final drive assemblies, constructed using the same herringbone gear principles as its transmission, demonstrated remarkable durability even under the intense conditions of sustained combat. When examined decades later, many Sherman tanks still had final drives that required no mechanical restoration after years of storage, a testament to the robust margins of safety built into the design. The conservative engineering approach, with generous tolerances and sturdy components, meant that these systems could withstand conditions that would typically destroy their German counterparts. By late 1943, The wealth of data collected at Kumdorf allowed engineers to compile comprehensive internal reports that circulated among the Wehrmacht's technical branches. These reports, intended for high-ranking officers and officials in the German Ministry of Armaments, painted a clear and sobering comparison of the two nations' technological capabilities. They underscored that the American automotive engineering, marked by maturity and innovation, was fundamentally ahead of German efforts, despite the latter's reputation for scientific expertise and meticulous design. While German manufacturing prioritized tight tolerances and precision engineering, American mass production techniques embraced a more pragmatic approach, tolerating looser fits that often would be considered subpar in German factories. Paradoxically, this trade-off resulted in tanks that were more reliable and better suited for battlefield conditions. The use of interchangeable parts further simplified field repairs, allowing maintenance crews with basic tools and limited specialized training to quickly address issues and keep the vehicles operational. These differences in production philosophy and engineering approach helped the American tanks outperform German designs in durability, reliability, and operational endurance, key advantages in the brutal realities of war. While German military vehicles demanded factory-level precision and specialized equipment for many repairs, their entire design philosophy was rooted in a fundamental priority: ensuring operational reliability over chasing after maximum performance specifications that, while impressive on paper, proved difficult to maintain and sustain in the chaos of combat. The Germans focused heavily on creating vehicles that could withstand the rigors of battlefield conditions, even if that meant accepting certain limitations in achieving peak technical metrics. In contrast, the United States brought to bear a vastly different approach, influenced by long-standing civilian automotive industry experience that far exceeded German capabilities in scale and scope. Internal assessments conducted by German engineers during the war consistently highlighted American industrial advantages that went beyond mere production figures. American automotive engineering, built upon decades of mass production, innovation, and widespread civilian vehicle ownership, exemplified a level of maturity and versatility that Germany had not yet cultivated. Prior to the outbreak of hostilities, the United States had cultivated a culture where automobiles were ubiquitous, owned by people across all walks of life: farmers, workers, professionals, and middle-class families alike. Vehicles in the American landscape were commonplace, serving as essential tools for daily life. By contrast, Germany's experience with civilian automobiles remained quite limited. For many years, cars were considered a luxury reserved for the wealthy elite and high-ranking party members. The ambitious Volkswagen program, which had been envisioned as a means to put affordable cars into the hands of ordinary Germans, struggled to deliver on its promise. By 1939, fewer than 1,000 civilian vehicles had been produced, a stark indicator of Germany's limited civilian automotive industry at that time. This significant disparity in the maturity of the automotive industries deeply influenced the philosophies behind tank design in both nations. American engineers developed tanks that could be maintained by personnel with skills similar to those required for civilian vehicles, mechanics who understood standard automotive principles. Their focus was on ensuring that the tanks could be repaired swiftly and efficiently, often using parts and procedures familiar from civilian automobile repair, thus facilitating rapid maintenance even in the field. Meanwhile, German tank design prioritized specialized craftsmanship and required technicians with extensive military technical training. These vehicles demanded expert attention and complex, often proprietary, repair procedures that could only be performed by highly skilled specialists. Consequently, German tanks often suffered from reliability issues, especially during long or intense campaigns. By late 1943 and into 1944, field reports made it increasingly clear that German tanks' reliability was a major concern. The Panther tank, one of Germany's most formidable designs, exemplified these difficulties. To prevent catastrophic mechanical failures during combat, Panther crews had to follow strict operational restrictions. Drivers were explicitly instructed to limit gear changes. Excessive shifting would damage the transmission. The third gear, in particular, was prone to frequent failure, and field manuals warned against using it unless absolutely necessary. Furthermore, Panthers could not turn while moving in reverse without risking serious damage to the transmission, an operational limitation that restricted tactical maneuverability. Pivot turns, a maneuver that allows a vehicle to rotate sharply on the spot, were only possible under ideal conditions, specifically, when the ground resistance was equal on both tracks, thus severely limiting tactical options on the battlefield. Random debris or foreign objects entering the running gear posed further problems, as they could jam the drive sprocket, requiring hours of painstaking maintenance and repair. All these issues persisted despite the fact that Panthers were assembled in dedicated tank factories by skilled workers using the best materials Germany could supply. The design and manufacturing processes were advanced, yet the fundamental weaknesses in reliability remained evident. In stark contrast, the American approach to tank design leveraged the mass production of civilian automotive components, a strategy that proved remarkably effective. The Sherman tank, for example, was the result of collaborative efforts by engineers from major automotive firms such as General Motors, Ford, and Chrysler. These companies applied their extensive experience in civilian vehicle manufacturing, utilizing principles of mass production and standardization that had been perfected over decades. The Sherman incorporated commercial-grade automotive parts wherever feasible, transmissions, engines, and other components, drawing from a broad supply chain that included manufacturers like Caterpillar Tractor, Buick, and Ford. These parts were manufactured to strict, identical specifications, making them interchangeable without the need for adjustments or extensive repairs, significantly easing maintenance in the field. This standardized approach not only enhanced reliability but also allowed repairs to be performed quickly and with readily available parts. While standardization of this nature was routine in the American automotive industry, it remained largely unattainable in German tank manufacturing, where precision engineering and custom components often meant repairs were more complex, time-consuming, and less predictable. The contrast in manufacturing philosophies reflected the broader difference in industrial maturity and logistical capability between the two nations, fundamentally shaping the operational effectiveness and reliability of their armored forces in the difficult circumstances of wartime. During World War II, American tank production was characterized by a high degree of variability, as each manufacturer introduced subtle modifications to their vehicles. These variations, while seemingly minor, prevented the true interchangeability of parts across different batches and models, leading to a complex logistical landscape. Over the course of 1943 and 1944, additional captured tanks, including several Shermans taken from British units fighting in Italy as well as Soviet forces on the Eastern Front, were brought into the United States Army's engineering and testing facilities. These captured vehicles were subjected to rigorous evaluation procedures, which aimed to understand their capabilities and gather detailed data on performance across various production periods and configurations. This process of testing and evaluation resulted in the creation of an extensive database, offering a comprehensive overview of American tank performance. It included insights into how different variants fared in combat, how they evolved over time, and what issues they faced during operations. Notably, The British adapted some of their Sherman tanks by mounting their own 17-pounder anti-tank guns, an effort to address one of the Sherman's primary weaknesses, which was its comparatively limited firepower. This modification produced the Firefly variant, which became a formidable asset against German armor. German engineers closely scrutinized these modified Shermans, paying particular attention to how the tank's large turret rings could accommodate the bigger guns with minimal structural changes. They were intrigued by the fact that the original Sherman design possessed a built-in capacity for growth, which had not been fully appreciated when these tanks were initially designed and deployed. The Firefly demonstrated an impressive potential for upgrades, a feature that German designers had not foreseen when specifying their own vehicles. This adaptability made the Sherman an unexpectedly versatile platform. In contrast, the German Panther tank was developed in a rushed manner, primarily to counter the Soviet T-34, which had proven highly effective on the battlefield. However, the Panther's design limited its capacity for significant armament upgrades without a complete overhaul of its turret and chassis. Recognizing the importance of reliability in combat, the Allied engineers expanded their testing programs to include extensive reliability trials. These tests aimed to simulate the harsh conditions tanks faced in the field. Testing teams drove the Sherman tanks over hundreds of kilometers of rough, cross-country terrain, meticulously documenting every mechanical issue, maintenance need, and component failure they encountered. The goal was to understand how these vehicles held up under simulated combat stress. The results from these trials were then compared with field reports from Panther and Tiger units operating on both the Eastern Front and in Italy, providing a clear picture of relative reliability. The data painted an unambiguous story about the operational readiness of these vehicles. Throughout most of 1943, Panther tanks had an average operational readiness rate below 40%. In some units, the situation was so dire that fewer than 1 in 4 tanks was capable of engaging in combat at any given time. Mechanical failures and maintenance issues kept Panther units grounded far more often than their Allied counterparts. The situation was documented in meticulous detail within German field reports, which highlighted the structural and mechanical weaknesses that plagued the Panther. For instance, during the pivotal Battle of Kursk in July 1943, an operation known as Operation Citadel, the Panther units achieved only a 16% operational readiness rate. Mechanical failures frequently rendered more tanks inoperable than enemy fire did. By the end of that year, in December 1943, the readiness rate had only modestly improved to 37%. The trend of slow progress continued into early 1944, with reports from February indicating a 37% readiness level. By April, a small increase was observed, reaching 50%, and finally, by May of 1944, operational readiness had climbed to an impressive 78%. These figures represented the proportion of Panthers available and ready for combat on any given day, with the remainder of the tanks either awaiting replacement parts or undergoing repairs. The steady upward trend over these months reflected efforts to address design flaws, improve maintenance procedures, and enhance mechanical reliability. Nevertheless, even the best Panther readiness figures never quite approached the levels achieved by the Sherman tanks during their initial production phase. By December of 1943, it had become undeniable to any objective observer analyzing the extensive data that the Panther's mechanical reliability was a significant weakness. The lifespan of its engine was notably limited, with the diesel-powered version barely covering 3,000 kilometers under proper maintenance regimes. In stark contrast, the Sherman diesel variant reliably exceeded 3,000 kilometers, demonstrating a clear advantage in operational longevity and maintenance cost efficiency. The Panther's engine life, on the other hand, rarely surpassed 1,000 kilometers before requiring significant repairs or overhaul, an issue that severely affected the tank's combat availability and logistical sustainability. After several rounds of improvements, the most pressing early issues had been effectively addressed, leading to noticeable enhancements in the performance and durability of the tanks. Reports from German military sources in March of the year 1944 documented that the upgraded engines of the Panther tank were now capable of achieving a service life spanning roughly 700 to 1,000 kilometers. These findings were considered a significant success at the time, reflecting the ongoing efforts to improve the durability of German armored vehicles amidst the relentless pressures of wartime production and combat conditions. However, this advancement in Panther engine longevity only brought their overall operational endurance to approximately one-third of what was achievable with the diesel-powered Sherman tanks. The Sherman's transmission system, for instance, was known for its remarkable reliability. It required minimal maintenance between overhauls and featured synchronized gears that significantly reduced the likelihood of mechanical damage caused by driver error. The design of the Sherman's transmission allowed for smoother shifting, which in turn made it less susceptible to operational failures caused by improper handling. In stark contrast, the Panther's transmissions demanded a constant and careful attention from the crew, with frequent repairs necessary to keep them operational. One of the most common issues was the failure of the third gear, which was so widespread that drivers often resorted to skipping gear ratios altogether, shifting directly from second to fourth gear, to bypass the problematic third gear. This makeshift tactic was a testament to the persistent mechanical challenges faced by Panther crews, who had to adapt their driving techniques to accommodate their vehicle's fragile transmission system. The reliability of the final drives, an essential component of a tank's mobility, also differed markedly between the two models. The Sherman's final drives consistently operated reliably, even under conditions that routinely destroyed Panther final drives within just 100 to 200 kilometers of use. Field reports from German units that had captured and employed Sherman tanks confirmed the data gathered from Kumdorf testing stations. These real-world accounts underscored the practicality of the Sherman's mechanical robustness. German mechanized units, in particular, displayed a strong desire for dependable vehicles, especially as their own tank crews and infantry formations faced increasing deterioration and attrition. In their desperation, they eagerly made use of any captured American tanks, Sherman's included, that remained intact. Unlike the Soviet T-34 tanks, which the Germans frequently modified extensively before putting them into combat, the Shermans entered German service largely untouched, as they demonstrated correct operation straight out of the factory without needing fundamental modifications. The design excellence of the Sherman meant that it worked as intended, without the fundamental flaws that had plagued many other tanks. German tank crews, many of whom had experienced multiple mechanical failures with their own vehicles, found the Sherman's reliability to be nothing short of remarkable. These crews often expressed their admiration and surprise in letters and official reports, noting that the Sherman's steady performance freed them from constant mechanical concerns and allowed them to concentrate more fully on tactical and operational considerations. In fact, reports from panzer regiments reveal that Sherman operators were able to focus their efforts on battlefield tactics and overall combat effectiveness because they were not burdened by ongoing mechanical issues. Meanwhile, crews operating Panther and Tiger tanks constantly worried about the risk of breakdowns en route to or during their missions. The fear of being immobilized by mechanical failure was a persistent concern that hampered their operational rhythm and readiness. In January of the year 1945, during Operation Nordwind, the 10th SS Panzer Division captured 12 M4A3 Sherman tanks at Hellesheim. These tanks, which originally belonged to the American 43rd Tank Battalion, had been abandoned during the German assault and were then taken intact. The captured Shermans, each still in operational condition, were subsequently integrated into the division's ranks as the 12th Company of the 10th SS Panzer Regiment. From that point onward, they served actively in combat roles for the remainder of the war, primarily functioning as reconnaissance vehicles and mobile reserves. These roles demanded relentless mobility without the luxury of frequent maintenance stops, emphasizing the importance of mechanical reliability. German commanders quickly recognized what the Kumdorf testing had proven years earlier. American tanks were capable of performing reliably when it truly mattered. This dependable mechanical performance, more than firepower or thick armor, ultimately dictated the tactical utility and battlefield effectiveness of the Sherman in the final months of the conflict. A Sherman arriving at the front lines with a fully operational gun was infinitely more valuable than a Panther with superior firepower. That broke down 20 kilometers behind the lines. As the Wehrmacht retreated across multiple fronts in January of the year 1944, expanded testing programs were initiated, and additional captured equipment was brought to Kumdorf for examination. Engineers meticulously analyzed the Sherman's components, including the M4A1 variant equipped with the Continental R975 radial engine, to better understand and improve their operational capabilities. Through these ongoing evaluations, the true significance of the Sherman's reliability became even clearer, further cementing its reputation as a battlefield workhorse that could be depended upon amid the chaos and destruction of late-war combat. The detailed examination of various tank models revealed a common thread. Each variant shared a core set of characteristics that set them apart from many of their contemporaries. Among these, the M4A2 stood out due to its twin General Motors 6046 diesel engines, a configuration that drew particular attention from military engineers. Tests conducted on this model highlighted its notable efficiency in fuel consumption, which surpassed that of many gasoline-powered counterparts, while also showcasing distinct operational behaviors that set it apart in terms of power delivery and reliability. Similarly, the M4A3 variant equipped with the Ford GAV8 gasoline engine garnered high praise, especially from American crews who regarded it as the most effective power plant fitted to Sherman tanks during the war. Each variant, despite differences in engines or configurations, demonstrated a startlingly consistent level of automotive reliability, an outcome that could be attributed to meticulous engineering and strict manufacturing standards. This universal dependability was so pronounced that it caught the attention of German engineers, who were accustomed to significant inconsistencies between vehicles produced by different manufacturers, even when these vehicles were nominally identical. Particularly impressive to the German military observers was the diesel-powered M4A2, which they examined thoroughly at Kumdorf. The Soviet forces, in the course of their war efforts, received around 4,100 tanks of this type through Lend-Lease programs, and a considerable number fell into German hands during retreats on the Eastern Front. The twin GM6046 diesel engines in this model offered performance that could match any Sherman variant, with the added benefit of markedly reduced fuel consumption compared to gasoline engines, a factor of critical importance as German fuel supplies became increasingly scarce and difficult to replenish. The German engineers had dabbled in developing their own diesel tank engines, but their efforts were ultimately abandoned due to the complexities involved in manufacturing such systems and the intricate nature of fuel injection technology. In contrast, American industry managed to produce diesel-powered Shermans alongside the traditional gasoline models without severely disrupting production lines. This flexibility demonstrated not only advanced manufacturing capabilities but also a level of technological sophistication that German industrial efforts could not match during the wartime period. By March of 1944, reports circulated from General Heinz Guderian, the Inspector General of Panzer Troops, who noted in official communications that the reliability of the Panther tank had improved to levels deemed acceptable. The lifespan of the Panther's engine had increased to between 700 and 1,000 kilometers, and issues with the final drive had been largely resolved thanks to systematic design modifications and enhanced manufacturing processes. Although these improvements marked a notable success for German engineering, they also underscored how the Panther, which had once been a formidable adversary, had only just reached the reliability levels that the Sherman tanks had possessed from their very inception, back in 1942. This realization cast a harsh light on the stagnation and setbacks faced by German armored vehicle development. While American tanks had consistently maintained high standards, the German industry struggled increasingly with resource shortages and the relentless pressure of Allied strategic bombing campaigns. These attacks targeted critical points in the production chain of German armored vehicles, including the manufacturing of engines and transmissions. A particularly devastating blow occurred on the night of April 27 to 28, in 1944, when the Royal Air Force Bomber Command launched a meticulously planned raid on the Maybach engine plant in Friedrichshafen. Involving a fleet of 322 aircraft, this attack was described by the archives of the Imperial War Museum as the most damaging raid against German tank production during the entire war. The strike not only destroyed the engine factory but also obliterated the adjacent ZF gearbox plant, causing a complete halt in the production of tank engines and transmissions. The consequences of this raid were severe, crippling the supply of crucial components and further undermining the German armored forces' ability to maintain and produce effective tanks amidst the ongoing conflict. Over the course of approximately 6 months, the situation within German tank production facilities deteriorated considerably. When manufacturing activities finally resumed in November of the year 1944, it was painfully evident that the quality control standards had suffered a significant decline. In an effort to compensate for the dwindling workforce caused by widespread conscription into the German military, industry increasingly relied on forced labor, which, unfortunately, led to the intentional sabotage of critical components. For example, sabotage efforts included jamming cigarette filters into oil passages to cause blockages, and the improper installation of gaskets, which compromised the integrity of vital systems. Parts were assembled without adhering to proper clearances, further undermining the reliability of these weapons systems. This level of manufacturing defect and neglect, however, did not extend to the production of American tanks like the Sherman, which were manufactured in well-protected factories located deep within the United States. These factories were far from any combat zones and operated under conditions that motivated workers to produce high-quality components, earning fair wages and working in decent circumstances. The fundamental distinction between American and German tank production was not rooted in differences in engineering expertise or knowledge of automotive principles but rather lay in the contrasting levels of industrial capacity and the underlying design philosophies guiding the two nations. German engineering teams possessed extensive theoretical knowledge and scientific understanding comparable to that of their American counterparts. They understood automotive principles thoroughly but had a tendency to apply them inconsistently during tank design. Instead, they often prioritized other factors such as maximizing armor thickness and offensive firepower, which resulted in impressive specifications on paper but often translated into poor reliability and operational issues in actual combat conditions. The Panther tank, for instance, was equipped with a powerful 75mm KWK-42 gun and formidable frontal armor designed for offensive dominance. However, these advantages came at the expense of an overburdened powertrain that struggled to reliably support the vehicle's weight of approximately 45 tons. Similarly, the Tiger tank, known for its formidable firepower and heavy armor, required a highly complex maintenance regime. Its complex mechanical systems demanded frequent repairs, performed by specialists with advanced training, something difficult to sustain given the wartime shortages of skilled personnel and spare parts. These compromises might have been tolerable if German industry had been able to produce sufficient quantities of vehicles and essential replacement components. However, the reality was quite different. As Allied bombing raids intensified and resource shortages worsened, German manufacturing capabilities further declined. Their factories, which once had the capacity to produce tanks in the hundreds, increasingly struggled to meet demand. In contrast, American engineers, with decades of experience in civilian automotive mass production, designed tanks that could be produced and maintained on an entirely different scale. These vehicles were intended to be manufactured by the tens of thousands and maintained by mechanically skilled personnel who had learned their craft in civilian industries. The Sherman tank exemplified this pragmatic approach. Its powertrain incorporated components that had already proven reliable in commercial vehicles, and its design drew heavily from the principles of automobile and truck manufacturing. An especially notable feature was its electrical system, which included a backup generator capable of powering turret traverse even when the main engine was disabled, something that German designers regarded as an unnecessary luxury but one which proved to be invaluable in combat. German tank crews could only dream of such convenience and redundancy, especially those who had experienced firsthand the agony of turret traverse failure when engines stalled on slopes or during prolonged maneuvers. These features, however, were not included in German technical specifications, as their design priorities heavily favored armor protection and firepower over crew comfort or system redundancy. By the spring of 1944, reports from Wehrmacht units across all fronts confirmed that mechanical problems were becoming increasingly common. The quality of manufacturing had continued to decline, and the availability of spare parts was shrinking sharply. The Panther, for example, was so mechanically fragile that its final drives could not withstand sustained road marches exceeding 100 kilometers. As a result, field commands issued strict orders limiting Panther movements to shorter distances, often restricting their deployment to rail transport for longer relocations. Throughout this period, the difference in industrial capacity and design philosophy between American and German tank production became starkly apparent. While German tanks prioritized maximum firepower and armor, sometimes at the expense of mechanical reliability, the American approach emphasized rugged, efficient, and maintainable machinery. This strategic divergence reflected deeper underlying differences. American industry's focus on mass production, standardization, and ease of repair, versus Germany's emphasis on technical perfection and tactical advantages in design, often compromised by wartime shortages and degraded manufacturing conditions. During the critical period leading up to and including the summer of 1944, German military engineers and tacticians began to recognize a stark reality. The United States and its allies had mastered not only the art of mass-producing armored vehicles but also the science of creating remarkably reliable and durable tanks that could withstand the rigors of wartime conditions. This realization drew attention to the importance of deploying vehicles that could endure prolonged operations without succumbing to mechanical failures, which, in many cases, proved more devastating than enemy fire during march phases and combat engagements. In this context, one particularly telling example was the development of the Berger Panther recovery vehicle. Built upon the same chassis as the formidable Panther tank, this support vehicle was intended to facilitate the retrieval and repair of disabled Panthers on the battlefield. Yet, it shared the same fundamental reliability issues that plagued the Panther itself. Despite its purpose and robust design intentions, the Berger Panther often suffered from the same mechanical problems, breakdowns and failures, that had already compromised so many German tanks. This commonality underscored a troubling pattern. Even auxiliary vehicles built on the same platforms were not immune to the systemic reliability problems that undermined the operational effectiveness of the German armored force. The harsh reality faced by German commanders was that mechanical failures were responsible for an alarmingly high percentage of tank losses. In some units, reports indicated that as many as 70% of tanks lost in combat were actually lost not because of enemy action, but due to breakdowns or mechanical failures. These failures often incapacitated vehicles during marches or prolonged operations, reducing their availability and combat readiness at crucial moments, thereby eroding the tactical advantage that armored vehicles were supposed to provide. Contrasting sharply with German shortcomings was the relentless production of American tanks, particularly the Sherman, which continued at an unprecedented rate throughout the war. The United States industrial complex proved capable of manufacturing vast quantities of Shermans with remarkable efficiency and speed. In fact, American factories produced more than 49,324 Sherman tanks during the course of the conflict, an output that surpassed the total tank production of all types combined by the entire German military industry. This staggering scale of production meant that the Allies could sustain operations and replace losses with relative ease, maintaining numerical superiority in armored vehicles across various theaters of war. Moreover, the British Commonwealth forces benefited significantly from the Allies' Lend-Lease program, acquiring thousands of Shermans to bolster their armored strength. The Soviet Union, too, received an impressive number of over 4,000 diesel-powered Sherman variants. Meanwhile, in the dense jungles and rugged terrains of Burma, Chinese forces employed Shermans with devastating effect against Japanese armor, which was technologically inferior to both American and German designs. Regardless of the theater, be it Europe, Asia, or the Pacific, the consistent success of the Sherman underscored a vital truth. When properly maintained, Shermans could outperform many German tanks under harsh operational conditions, a fact that was firmly validated through a series of meticulous tests and battlefield reports. The durability and reliability of the Sherman were widely praised by those who operated and maintained them. German tank crews, after capturing and subsequently using Shermans, consistently commended their automotive engineering and dependability in various correspondence, combat reports, and post-war interviews. Reports from the Eastern Front further confirmed this sentiment, revealing that even the complex Chrysler 57 multi-bank engine, with its 5 separate engine blocks, was notably easier for German mechanics to troubleshoot and repair compared to the more intricate German tank engines. The latter often demanded specialized knowledge, tools, and procedures, which slowed down repairs in the field and increased downtime. The Ford GAA V8 engine, an American power plant lauded by Allied crews for its robust reliability and substantial power output, also impressed German technicians, who found it to be remarkably dependable, especially when compared with the Maybach engines traditionally used in German tanks. The Maybach engines required constant adjustments to valve clearances, ignition timing, and carburetor settings to function optimally, often making repairs labor-intensive and time-consuming. In contrast, the Ford GAA engine's resilience and straightforward design meant that it could operate effectively under diverse and demanding conditions with minimal maintenance. Likewise, the General Motors twin diesel engine, initially dismissed by the U.S. Army as less reliable than its gasoline counterparts and therefore only produced in limited quantities for Lend-Lease, surpassed all expectations. It demonstrated superior performance and reliability compared to the German diesel engines, which, although advanced for their time, did not match the durability and power output of the American design. The generous design margins incorporated into the Sherman's components, particularly the transmission and final drive, were a strategic advantage. These components, initially specified for the 40-ton M4 with 400 horsepower, required no significant modifications to handle the heavier, more heavily armored 70-ton M4A3E2 jumbo assault tank with its substantially increased armor protection. The same transmission and drive components that managed the standard Sherman's 451 horsepower engines also successfully transmitted 650 horsepower from experimental engines, operating reliably without failure or the need for reinforcement. German amazing machinery and imposing armor faced a far graver challenge that went well beyond the limitations of individual vehicle performance. While a tank's technical specifications were important, the broader strategic and logistical realities played a decisive role in determining the outcome on the battlefield. The overwhelming superiority of American artillery, their unmatched close air support capabilities, and a logistics network capable of supplying vast quantities of ammunition, fuel, and replacement parts created a situation where German armored forces, regardless of their tank models or tactical brilliance, were often rendered ineffective. In particular, the durability and dependability of the Sherman tank stood out as a pivotal factor that allowed American armored units to maintain relentless pressure and continuous operations, something which German panzer divisions found increasingly difficult to achieve. American tank formations were able to launch aggressive attacks, sustain prolonged combat engagements, pursue retreating enemies, and swiftly reorganize for subsequent operations, all without frequent, time-consuming maintenance stops. This operational agility was grounded in the Sherman's remarkable reliability, a trait that allowed American forces to keep their tanks on the offensive far longer than their German counterparts could sustain theirs. In contrast, the German panzer divisions were forced to carefully ration their limited fleet of operational vehicles, calculating each move with the awareness that every act of movement drained precious remaining mechanical life, pushing their tanks ever closer to failure due to wear and tear. The constant pressure to conserve operational vehicles, while managing the risk of mechanical breakdown, significantly hampered their tactical flexibility. This stark difference in the availability of operational tanks directly influenced the capacity of each side to maintain offensive momentum. The side with greater vehicle readiness could apply sustained offensive pressure, while the adversary had to ration their limited resources carefully, often dreading the moment their remaining vehicles would fail at a critical point. From the German perspective, their effort to incorporate captured American Shermans into their own operational arsenal served as conclusive proof of American automotive engineering superiority. During the fierce Battle of the Bulge, specifically in December 1944, the 150th Panzer Brigade, which was created explicitly for infiltration and sabotage behind enemy lines, endeavored to acquire and utilize captured American tanks to bolster their efforts against the Allies. German military planners selected the Sherman primarily because of its well-earned reputation for dependability and robust design. Yet, despite their interest, the brigade managed to obtain only 2 Sherman tanks, and of these, merely one was in sufficiently good condition to be considered operationally useful. Regrettably, even this single functioning Sherman never made it into combat. Due to overwhelming traffic jams, logistical bottlenecks, and severe infiltrator movement disruptions, the operation was unable to fulfill its objectives. The strategic goal of penetrating deep behind enemy lines with reliable armored support was thwarted by the very vehicles meant to facilitate success, highlighting that, in such high-stakes behind enemy lines missions, only American equipment presented any realistic chance of success, owing to their proven durability and reliability. German tanks, even when fully operational, could not guarantee the sustained and dependable performance required for such complex and perilous missions. The realization of this shortcoming was made official on the 23rd of January, in the year of 1945, when the German military's Panzer Commission convened and produced a comprehensive report that laid bare the scale of their automotive failures. The report detailed a catastrophic number of final drive failures across all German tank models. The findings were stark and disheartening. Prior to their crushing Eastern campaign, there had been approximately 500 failures in the Panzer IV tanks, about 370 in the Panther model, and roughly 100 in the Tiger series. Furthermore, around 200 failures had also been documented in the Hetze tank destroyers, which were based on the Czech 38-ton chassis, a vehicle not originally designed to withstand the rigorous demands of prolonged combat. The insights provided by high-ranking officers such as General Wolfgang Thiemann, who served as the Chief of Staff for the Panzer Troop Inspectorate under the command of General Guderian, were equally sobering. Thiemann and others explained in unambiguous terms how these mechanical failures profoundly hampered operational effectiveness. In such circumstances, the disciplined and efficient utilization of tanks became virtually impossible. The mechanical unreliability shook the confidence of the crews, leading to a decline in morale. In many instances, crews abandoned entire tanks simply because they feared that, due to critical final drive malfunctions, they would become stranded behind enemy lines and risk capture or destruction. German tanks, engineered to project menace through their formidable appearance and tough armor, were now plagued by fundamental mechanical issues that undermined their very purpose. The fundamental shortcomings in the specifications of armored vehicles became glaringly evident, especially when it came to their mechanical reliability, which is arguably the most critical aspect for operational success. To be truly effective in combat, a tank must reliably reach the battlefield, endure the rigors of battle, and complete its missions without failure. This core requirement was sorely neglected in many designs. In early 1945, as Soviet forces relentlessly advanced toward Berlin, the Kumdorf testing facility was forced into a hurried evacuation. Engineers there frantically gathered all their testing data, carefully packed technical documentation, and shipped it off to more secure locations further west, with the hope of preserving vital intelligence for future analysis beyond the war. During this chaotic period, some of the captured tanks, including at least 2 of the American-made Sherman tanks, were pressed into combat service. These vehicles were thrown into the fray alongside German units, fighting desperately to defend the approaches to Berlin. These instances offered a rare and valuable opportunity to observe how tanks performed under actual combat conditions, providing an unfiltered comparison between different designs in the crucible of battle. The Shermans continued to operate until they were either knocked out by enemy fire or abandoned because their fuel supplies were depleted and they could no longer sustain movement. Meanwhile, German tanks, such as Panthers and the few remaining Tigers, frequently suffered breakdowns from mechanical failures at an alarming rate, failures that even seasoned crews, used to poor reliability, found shocking. The story of War Daddy 2, along with dozens of other Shermans tested at Kumdorf, exemplifies one of the most significant industrial disparities of the Second World War. German engineers, operating within a system that prioritized perfect theoretical design over practical durability, produced tanks that appeared formidable on paper but ultimately failed in sustained field operations. Their engineering efforts resulted in vehicles that, despite their impressive specifications, could not withstand the rigors of actual combat. Conversely, American engineers, drawing on decades of automotive manufacturing experience, designed tanks that, although lacking some of the advanced technical features favored by their German counterparts, proved to be reliably functional under the harsh conditions of frontline service. In armored warfare, and in military operations in general, the ultimate advantage belongs to the weapon system that functions flawlessly when needed, rather than the one that might be superior in theory but cannot reach the battlefield or complete its mission due to reliability issues. Post-war analyses conducted by both American and British intelligence agencies confirmed the conclusions drawn from the German testing at Kumdorf. Their systematic examination of destroyed German tanks revealed that mechanical failures occurred with as much frequency as combat damage as reasons for losing vehicles. Final drives would break under stress, transmissions would seize due to inadequate lubrication or operator error, and engines would burn out from overheating or lack of oil. These failures highlighted a critical flaw: German engineering's obsession with creating the most advanced and impressive technical specifications often blinded them to the importance of reliability and ease of maintenance. German engineers had constructed tanks that no ordinary mechanic, especially conscripted personnel, could repair without extensive specialized training. Their engines demanded constant expert attention from skilled technicians, and the logistics system supporting these tanks was fragile, collapsing under the overwhelming demand to supply a vast array of unique spare parts to widely dispersed units. The combined result was a vehicle that, despite its formidable appearance and impressive specifications, was often unusable in the field because it could not be maintained or repaired reliably. These bitter lessons learned at Kumdorf significantly influenced post-war German tank design philosophies, particularly in West Germany's Bundeswehr. When the Federal Republic began developing the Leopard 1 main battle tank in the 1950s, the design team consciously shifted their focus. They emphasized creating a vehicle that prioritized reliability and maintainability over the pursuit of the most cutting-edge technical features, understanding that in modern armored warfare, the ability of a tank to operate effectively when needed outweighs the allure of theoretical superiority. The performance specifications of these military vehicles reveal a thoughtful integration of American automotive engineering principles, consciously adapted to meet the demands of armored warfare. Engineers studied and drew lessons from civilian automotive design, emphasizing durability, reliability, and ease of maintenance, and then deliberately incorporated these philosophies into the development of their military hardware. The result was exemplified most notably by the Leopard 1 tank, a vehicle that embodied many of these tried and true engineering tenets. Its design featured a robust powertrain that was engineered with substantial safety margins, ensuring that the tank could operate effectively under the strenuous conditions of combat without frequent breakdowns. Moreover, the Leopard 1 was designed for simplicity and practicality, making routine maintenance straightforward and achievable with minimal reliance on specialized tools or spare parts. This approach meant crews could perform repairs in the field rapidly, minimizing downtime and increasing operational readiness. The vehicle also incorporated standardized components, which allowed for quick replacements and repairs in the field, and it was engineered with a growth potential that facilitated future upgrades without necessitating a complete redesign of the entire platform. Such foresight in design contributed to the tank's longevity and its status as one of the most successful armored vehicles of the Cold War era, seeing service with multiple nations and enduring in production for several decades. This philosophy of engineering was exemplified in the context of captured enemy equipment, such as the Shermans at Kummersdorf, including the distinctive War Daddy II. Its name still boldly painted on the hull. Their presence represented far more than mere trophies for technical scrutiny. These tanks served as tangible evidence that industrial maturity and sound engineering principles, rooted in practical battlefield experience, held greater strategic importance than the pursuit of cutting-edge technical innovation that ignored manufacturing realities. They underscored a fundamental lesson: reliability, ease of maintenance, and manufacturing practicality often outweigh the allure of advanced but delicate technology. German tank designers, motivated by the belief that advanced specifications could compensate for material disadvantages and lesser numerical strength, pursued increasingly sophisticated and high-performance designs. They thought that superior technology, using the best materials and engineering, could provide the edge needed to counteract their operational disadvantages. However, this assumption proved fundamentally flawed. In contrast, American engineers, through years of battlefield experience, understood that the true strength of their vehicles lay in their reliability, ease of maintenance, and the ability to keep tanks operational over extended periods. They prioritized building vehicles that could be maintained effectively and operated consistently in demanding combat conditions, knowing that logistics, sustained operational capacity, and rapid repairability were the real determinants of victory. This pragmatic approach proved decisively successful. The reliability gap between the Sherman tank and its German counterparts influenced not only tactical armored warfare but also reshaped the broader strategic understanding of military-industrial capacity. It became clear that technical sophistication alone was insufficient. The ability to produce reliable, maintainable, and easily upgradable equipment in large quantities could determine the outcome of conflicts. At the outset of World War II, Germany entered the global conflict with many technological advantages, possessing scientific expertise and engineering knowledge that exceeded those of most opponents. Nevertheless, Germany lacked the industrial depth and sophisticated manufacturing infrastructure required to sustain these technological advantages through mass production across multiple fronts. Meanwhile, the United States, despite producing many weapons that were, in some respects, less technologically advanced, harnessed its vast industrial capacity to manufacture vast quantities of weapons, including tanks, aircraft, and artillery, in a sustained effort. They continually improved the quality, reliability, and performance of their equipment based on feedback from the battlefield, effectively integrating practical experience into ongoing production. The success of this industrial approach, exemplified by the design and production of the Sherman tank, was far more effective than concentrating solely on technological perfection for small-scale production. The United States produced nearly as many Sherman tanks as Germany produced all types of tanks combined, while simultaneously manufacturing enormous quantities of other weapons. This manufacturing capability enabled them to supply their allies through extensive Lend-Lease programs and maintained a high standard of living for their own population, even during the intense pressures of wartime. This economic and industrial capacity proved to be a decisive factor in the outcome of the war, surpassing the importance of battlefield victories alone. The ability to produce reliable and effective military hardware at an unprecedented scale, while continuously improving it, eventually proved just as critical as any single major engagement. The United States' vast industrial base, emphasizing reliability, mass production, and ongoing innovation rooted in practical experience, fundamentally shaped the course of history during the Second World War, proving that strategic industrial strength could influence the outcome of conflicts as much as tactical prowess on the battlefield. When viewed with pure objectivity, the stark simplicity of the situation was impossible to ignore. A Sherman tank equipped with a 75mm gun, which proved itself time and again on the battlefield, was infinitely more valuable than a Panther armed with a gun of purportedly superior caliber, but which often broke down long before it could engage the enemy. The Panther's impressive weaponry was rendered almost meaningless if the tank itself was unreliable, requiring days, sometimes up to 3, to be repaired for each day it spent in active operation. In essence, the operational effectiveness of a tank battalion depended heavily on the proportion of its vehicles that remained functional. A battalion operating at around 80% readiness could carry out missions that an entirely different unit, with only about 40% of its tanks operational, would find impossible to attempt. Reliability was far from a mere convenience or a secondary concern. It was the critical foundation upon which successful combat actions were built. Without dependable machinery, even the most advanced weaponry and well-trained crews could do little to influence the outcome of engagements. Throughout the course of the war, German tanks consistently failed this fundamental test of reliability and operational readiness. Despite their impressive appearances and advanced specifications, tanks like the Panther and Tiger frequently proved unreliable in critical moments. Conversely, American tanks, particularly the Sherman, consistently demonstrated high levels of dependability and ease of maintenance. By mid-1943, rigorous testing at the Kumdorf Proving Grounds had established this truth beyond any reasonable doubt. American tanks were far more reliable in the field than their German counterparts. While German commanders persisted in deploying Panthers and Tigers, their fearsome-looking machines, these vehicles often did not perform when most needed, undermining their battlefield effectiveness. The victory of the Sherman tank in World War II was not primarily due to its firepower or armor, which, although adequate, did not surpass that of German designs. Instead, it was driven by a different kind of superiority, industrial strength manifesting as mechanical reliability, consistent availability, and straightforward maintenance. German engineers, by mid-1943, recognized this reality through the results of exhaustive tests at Kumdorf. They compiled detailed reports that meticulously documented their findings, applying scientific rigor to every test. Their conclusions were clear. American advantages lay not just in raw design, but in the maturity of their industrial processes and manufacturing practices. However, knowing what the problem was and effectively solving it are two fundamentally different endeavors. German industry, burdened by resource shortages and the demands of a war on multiple fronts, lacked the capacity to reorient its entire production system toward prioritizing reliability. Meanwhile, American industry had spent decades refining its civilian automotive sector, embedding principles of durability, reliability, and ease of maintenance into commercial manufacturing. When the war began, they simply extended those proven principles from civilian cars into their military production lines, achieving remarkable success. The story of War Daddy II, an American Sherman tank captured in Tunisia and subjected to months of exhaustive testing at Kumdorf, embodied this industrial victory. Every component, every mile driven without failure, underscored a profound truth. German tank designs had taken a misguided path by emphasizing specifications over fundamental reliability. This single tank became a powerful symbol of the superiority of American industrial maturity and practical manufacturing experience over German engineering, which often focused more on impressive numbers than on consistent performance. Each test that affirmed American automotive excellence served as irrefutable proof that industrial maturity and accumulated manufacturing expertise held more value than theoretical performance metrics. These tests demonstrated that problems could be systematically solved through disciplined engineering and consistent production practices. Conversely, German engineers, in their focus on specifications and perceived technological supremacy, failed to recognize the importance of reliability as a core aspect of combat performance. In many ways, the tank itself was just one of thousands, some 49,000 in total, produced during the war. Its significance, however, transcended its physical form. It represented a devastating blow to German confidence and morale. It proved conclusively that Germany had already fallen behind in the industrial war, even as fierce fighting raged on. The capacity of American industry to produce reliable, durable machinery on such an enormous scale underscored a critical weakness in German war effort, revealing that their technological and industrial ambitions could not compensate for fundamental issues of practicality, reliability, and manufacturing discipline. In the end, the outcome was inevitably settled, irrespective of the level of German technical expertise or the strategic prowess displayed during the confrontation.